Howdy, today on Flipping Science we're looking at amines. So the science understandings we're going to look at, amines are classified as primary, secondary, or tertiary. Identify, name and draw primary amines containing up to 8 carbons in the main chain with 2 side chains and 1 or more amino groups. Amines act as bases, so draw the structural formula of a protonated amine and explain why the protonated form is more soluble than the parent amine.
The last group we're going to look at is amines. So amines contain a group with a nitrogen in it, usually attached to some hydrogens. This is a primary amine. That's the only ones that you need to be able to do in year 12. So there's a nitrogen usually attached to some hydrogens, and then there's a carbon that it's usually attached to. So the suffix here is amine, and if you need to indicate the location, then you use an infix to do that. So let's look at some examples. So down here, we'll start with this one down here. How many carbons are there? There's 1, so it's going to be meth. Now here's our amine group. There's no other location it can possibly be, so this is just methanamine. So methane, amine. So the parent carbon is methane with an amine group. If we look at this one now, so we'll number our carbons. So 1, 2, 3. So methyl, ethyl, propyl. So we're going to have prop at the top. So propan. Which carbon is the amine group attached to? It's on carbon 2, so propan 2, and then amine as our suffix. This one down here, now there's no carbon here, so we'll start numbering from there. 2, 3, 4, 5, 6. So it's going to be hexane, and on carbon 1, amine. So this last one here, we're going to number from here. The reason for that is we've got a side chain over here. The carbon that the nitrogen is attached to is carbon 2. So we'll number in 4, 5, 6. So we have 6 carbons in our longest chain. So I'm going to go hexane. On carbon 2, that's where our amine group is. And then the last bit is I've got a methyl group on carbon 4. So 4 methyl hexane 2-amine.
So what happens if you have more than one amino group? Well, you're going to need to change the suffix to indicate diamine and also number as well, because the amine could be on another carbon. So we have a look at our example down here. We've got 2 carbons in the chain, so we're going to have ethane. So ethane. And our amine groups are on carbon 1 and carbon 2. So ethane 1, 2, diamine. Okay, let's have a look at our second example here. This one's a little bit more complicated because we've got some methyl side chains. But let's find our longest chain. So 1, 2, 3, 1, 2, 3, so it's 1, 2, 3. So 1, 2, 3. So it's going to be propyl something. Methyl, ethyl, propyl. Now we've got 2 methyl groups on carbon 2. So we're going to go 2, 2. 2 methyl groups means we use the di prefix. Dimethyl. Methyl, ethyl, propyl, so propan. Now we need to indicate that the amino groups are on carbon 1 and carbon 3. So propan 1, 3, diamine. Okay? So amines are classified as either primary, secondary, or tertiary, and this is based on how many carbons are attached to the nitrogen in the amine. If nitrogen is attached to 1 carbon, that makes it primary. If it's attached to 2 carbons, then it's secondary. If it's attached to 3, that's tertiary. This is different from alcohols. In alcohols, you're counting the number of carbons that the carbon is attached to the hydroxyl group, how many carbons that one's attached to. Whereas with amines, it's just how many carbons are attached to the nitrogen. So I'm going to draw these so we can see what's happening. So we'll start with our first one. This is ethylamine. Let's start drawing that. So we've got 2 carbons, and then we've got our nitrogen at the end. We've got our hydrogen attached to the nitrogen. Okay, so primary. This nitrogen is attached to 1 carbon. So let's draw our secondary now. So we've got 2 carbons, then a nitrogen, then a carbon. So the 1, 2, 3, and then we'll put our carbon up there. I have to have our hydrogen down there. So put in our hydrogens. Okay, we got the angles a bit wrong around here, but you can get the idea. If we look at this nitrogen, we can see now that it's attached to 2 carbons. So nitrogen, 2 carbons there. Let's draw our tertiary. So we've got 2 carbons, then nitrogen, and we've got 2 methyls attached to that. So let's draw that one. So 1, 2, then we'll put in our nitrogen, then we'll put in our carbon up there, and a carbon up there. Now we'll fill in our H's. Okay, so now if we look at this one, we can see that the nitrogen is attached to 3 carbons, 1, 2, 3. So that makes it tertiary. So in many ways this is easier than judging if an alcohol is primary, secondary or tertiary. You're just simply counting how many carbons the nitrogen is attached to. So it's important to recognise that amines are bases. They're weak bases. They're Bronsted-Lowry bases because they can accept a proton. The reason for that is, we'll look at it with ammonia down here. Ammonia is similar to an amine, it's just you'd have a carbon chain attached to it. There's a non-bonding pair of electrons on the nitrogen in ammonia, and that means that any proton coming past can sit on here. But also that means that it can take the protons from, say, water going past and attach that there. So the hydrogen ion sticks to the non-bonding electron pairs, that gives it a full shell, but it's also got a positive charge because it didn't bring any electrons with it. So what that means is we get a positive charge overall on that. So if this was ammonia, it makes it ammonium, but in amines, it makes it a protonated amine. So let's have a look at that. So if we have our methyl ethanamine over here, we're adding our hydrogen ion to it, we can see that rather than having NH2, now we've got NH3, and we give that an overall positive charge. In terms of the arrangement of the 3D arrangement, you can now treat this nitrogen as if it's a carbon because we've got 4 things attached to it now. So this is attached to this carbon and 3 hydrogens, but it has an overall positive charge. When we represent the positive charge, we put the positive charge on the nitrogen when we draw a structural formula, and I'll show you that in a minute. So let's do a reaction with a hydrochloric acid. If you have ethanamine reacting with hydrochloric acid, we get the protonated amine here, and we get chloride ions. And this works exactly the same for secondary and tertiary amines. You're chucking in a hydrogen, and you're giving a positive charge to the nitrogen atom that's there. So let's do some examples. So an example question might be, draw the protonated form of these amines. So here's our amine, so we need to add in an H and give that an overall positive charge. So I'll draw, that's a pentagon, isn't it? Geez, that's not good. Nitrogen, I'm just going to pop my H in here. I'm going to have my CH3, CH3. And I'm going to put the positive charge on the nitrogen. It's not on the hydrogen, it's on the nitrogen, because that's where there's a lack of electrons there, and that's on the nitrogen. So all I'm doing is chucking in a hydrogen and putting a positive charge. Let's do the second one. So we've got a benzene ring, so we'll start by drawing that. Put in the double bonds, okay. So now I'm simply going to do NH2, and again I'm going to put the positive charge on the nitrogen. Then we'll connect in the rest of the chain. Okay. And then we're going to make this one NH3 and put the positive charge on the nitrogen. So there we go. Now let's just, for fun, classify these amines as primary, secondary or tertiary. How many carbons is this nitrogen attached to? 1, 2, 3. So this is a tertiary amine. So look at this one. How many carbons is this nitrogen attached to? 1, 2. So this would be a secondary amine. And this one here is at the end of the chain. So that nitrogen is attached to 1 carbon, so that makes it a primary amine. So much like carboxylic acids, amine drugs are often taken in the form of their salt. And the reason for that is its increased solubility. If it's in the salt form, you have your protonated amine down here. This protonated section has a full positive charge. That full positive charge makes it very, very soluble in water because you're going to get ion dipole bonding between water molecules and that full positive charge. So water is a polar molecule. It has a negative end and a positive end. The negative end is centered around the oxygen atom. So if we have our oxygen over here, it's going to be really, really, really attracted to the positive charge on the nitrogen atom there. It will be surrounded with water molecules, and that will allow it to dissolve in water. So remember, for solubility, you need to have some kind of interaction with the water molecule and be small enough to fit between the water molecules. In this case, due to the really strong attraction of the ion dipole attraction between the positive charge and the oxygen, we get strong attraction between that and water, and that makes it readily soluble in water. Now, if the amine is unprotonated, that means it can still form hydrogen bonds with water, which is what we see down here. So here we have an unprotonated amine. We can see we're getting hydrogen bonding between the oxygen of a water molecule and one of the hydrogens on the amino group. And over here we're getting attraction between the hydrogen of the water and the nitrogen in the amino group. So there is still hydrogen bonding, but a key point is that if an amine is protonated, it has much stronger attraction with water than if it's just the parent amine. The reason for that is that full positive charge. A full positive charge has a lot more charge and will attract a lot more of the negative ends of the water molecules, and that will increase the solubility. So the protonated amine is much more soluble than the parent amine. So let's look at an example. Amphetamine. There's methamphetamine. There's many different types of amphetamine. They're illegal drugs normally. They're usually restricted access by the government. This is a picture of it. And I'm going to ask you, what kind of amine is it? Is it primary, secondary, or tertiary? Okay, so it's a primary amine. So this nitrogen is attached to this carbon here. So it's a primary amine. It's not, when it's used as a drug, it's not in this form. It's as a salt. So you might have, say, a chloride ion attached here. So this would be NH3 plus with a Cl minus. That positive charge on the nitrogen makes it readily soluble in water. So even though there's a reasonably long carbon chain here, by protonating this and turning it into a salt, that makes it soluble in water. So the salt is in the tablet forms that are then taken by people who are using these drugs. I think it's very important to state that these drugs aren't a good idea to take. The safety aspect of them isn't great. It leads to all kinds of bad things happening. Some examples, just simply, this is from a site called Faces of Meth, where police were taking photos of people when they get arrested, and this is over the course of a very short period of time. This lady started using methamphetamine, so you can see just the changes to her physical structure, if nothing else. So it's not a good idea to take these, so I don't support that. So today on Flipping Science, we looked at amines, primary, secondary, tertiary amines, protonating amines, and how they're used as drugs, as salts. That's it for Flipping Science today. See ya.